Hello my dear students, welcome to physics classes by Sarabdeep Kaur Sidhu. So today's our topic is also a very important topic, and that topic is Clausius Clapeyron latent heat equation. And it's also, the topic is also, you can say, the applications of Maxwell's thermodynamic relations, and also we call this topic as change of state and Clapeyron equation. So the equation which we have to derive in this article, the equation is this, that partial derivative of P with respect to T at constant volume, that is equal to L over T V2 minus V1, where V2 is the final volume and V1 is the initial volume, and Vf also in sometimes it can be written as, instead of V2 there we can write Vf, that is the final volume, and V1, that is the initial volume. Clearly? And what is L here? L is the latent heat. And now question arises in the student's mind that what is this latent heat? So latent heat, I have told you that this topic is also called as change of state and this equation. So L is the latent heat, change of phase or change of state. So when there is a change of state from solid to liquid and liquid to vapor, then of a substance, then heat is supplied. So that heat supplied per unit mass, that is to change a phase of a substance, that heat is called latent heat. So how we can define, I have also write down this definition, that latent heat, the heat required to convert a solid into liquid or vapor. Clear? Means from liquid to vapor, or a liquid into vapor without change of temperature. Clear? Or we can say latent heat is energy released or absorbed by a body of thermodynamic system during a constant temperature. Okay? And during a constant temperature, and this process, or you can say during a constant temperature process, and we usually a first order phase transition occur. Clear? Constant temperature process, this is jointly clear. So this is about the latent heat. Mathematically, if you want to write that, L is equal to Q by M, where M is the mass and Q is the energy given to the substance for the change of phase, or energy released or absorbed during the phase change. Clear? And this L is latent heat of a substance. And when there is a unit mass, then this at unit mass, when there is a mass is for unit mass, or we can say 1 gram, then L is equal to Q. So this is about the latent heat. Then this what is represents by this equation. So this equation, you can say this equation is related, or you can deals with what? With change in boiling point, or freezing point. Boiling point or freezing point of a substance with change of pressure. Means if any, for example, water, if it is at boiling point, then when we change the pressure of that, then the temperature will also rise. Temperature, then there is also a change in you can say boiling point or freezing point of a substance with change of pressure. Clear? So this is about this representation of this equation, that this equation deals with this, that change in boiling point or freezing point with the change in pressure. So this is the, you can say, significance or anything of this equation. Then we have to derive. Now next question is how we can derive this equation. So there are two methods. First method we can also derive, but that is not in the syllabus of third semester BSc. So in third semester BSc we will derive this equation with the help of Maxwell's thermodynamic relations. So what are Maxwell's thermodynamic relations? So Maxwell thermodynamic relations, we know the Maxwell's thermodynamic relations. So with in that thermodynamic relations, the one relation that is Maxwell's, you can say second thermodynamic relation, and that relation is curly ds by dv at constant temperature is equal to dp by dt at constant volume, STPV. Clear? So this is a relation. Now if we, this is a Maxwell's relations, Maxwell's thermodynamic relation, second relation is this. Okay, second thermodynamic. Now if we multiply both sides by t, now multiply both sides by t, when you multiply both sides by t, we get ds, curly ds by dv at constant temperature, that is equal to t dp by curly dp by dt at constant volume. Clear? And we can take t inside this bracket. When we go inside, t ds by dv at constant temperature, that is equal to, yes, now this is equal to t ds by dv at constant temperature, this is equal to t curly dp by dt at constant volume. Now what is t ds? We know that according to second law of thermodynamics, second law of thermodynamics, what is TDS? TDS is equal to dq. So put here, we get dq by dv curly at constant temperature, that is equal to t dp by dt at constant. Clear? This we have. Now if we take this delta, now if we want to change the phase of that substance, for example this dq by dv, that gives this term, that gives the amount of heat absorbed or rejected per unit change in volume, of that substance at constant temperature. And this is also, sometimes it is also called latent heat. Clear? Now if we consider a body which changes its phase at temperature T. Now we consider a substance or a body which changes its phase at temperature T, and this absorbs the latent heat, that is L. Then V1, and we are taking, I am writing here, if we consider a substance or a body which changes phase and absorbed the latent heat, that is L, and V1 and V2 are the volumes initial and final, or you can say volumes of first and second phase, volumes of first and second phase. Yes, if these are the volumes of first and second phase, then we can write, what we can write, we can write this like this, that this is equal to L over V2 minus V1, that is equal to, if we are taking the mass, that is equal to 1 per unit mass, and taking the unit mass, then dq by m, that is equal to L na. Okay, so dq by, I have write dq by m, that is equal to L. If m we are taking unit mass, then dq, this is equal to L. That's why I am writing here L. So L over V2 minus V1, that is equal to T dp by dt at constant volume. So we get this equation. Clear? So this equation, L over V2 minus V1 over T dp by dt, this is called Clausius Clapeyron equation. Now there is also the third round of this, that if we consider, you can say, if we take, this is the equation L over, we have the equation L over V2 minus V1, that is equal to T dP over dt at constant volume. This we have. Now if we consider it for we consider that when this is the equation when the substance having 1 gram of substance, we are taking 1 gram of substance, and V2 is the final volume after phase change, and V1 is the initial volume. Clear? Or you can say V2 is the volume after phase change or after the substance absorb the heat L. Okay, and now at boiling point the vapor pressure is equal to saturated vapor pressure. So at you can say the special case of this, special case. What is the special case? At boiling point the vapor pressure is equal to saturated vapor pressure. Okay, or you can say that vapor pressure है जो, that is independent of volume. This is independent of volume. Then at that time we can write this equation as L over V2 minus V1, that is equal to T curly dP by dt at saturation or at saturated. Clear? So this is all about this equation, and this is called, this single at saturation, this is called Clapeyron equation. So this is all about this equation. So hope you enjoyed my lecture. So thank you very much.